Hello, I Dr. Vijay Chandra Jadala welcomes you to today's session on operating system. And today's topic is data integrity and protection, which is the most important topic in operating system related to the data security, data integration and protection. The general idea referred to data integrity and protection is to ensure that the data you put into a storage system is the same when the storage system returns it to you. In other words, the data stored should be same as of data retrieved. Data integrity makes sure that the data is valid. Protection, that is data protection, makes sure that the data is protected against loss and unauthorized access. In operating system, data protection is majorly depend on firewall systems, access control security policies and intrusion detection systems. Data protection is modern storage system focusing on checksum. So the data protection system in modern systems is focusing on checksum, which is the most important concept here. By using checksum only, we are going to identify the security uh, of the particular data as well as the integrity related concepts. So data protection in modern storage system is majorly focused on checksum implementing and usage. Different checksums protect against the types of faults. The most common used checksum here is using the XOR. By using XOR related checksum, we are going to check the data integrity as well as protection that related to the data security. So here data protection is nothing but whatever we give to the system, storage system, it should return it to us. As the reliability means depend confidently. We can say that we are reliable on the particular system when we depend. Reliability means depend confidently. When we will depend confidently, when it depend confidently, when the storage system which data we put in will return it to us. When it return as the same the data, then we can depend on the particular data storage system that is related to the data integrity and protection. So the common types of failures of disk failures are one is electrical failure, mechanical failure, logical failure, bad sectors failure. So the hard disk, in hard disk it's divided into different tracks and sectors. So and small sectors there will be blocks, and there is a chance of failure of these blocks. Then firmware failure, that means there will be a IC board on it, and this board software related software there is a chances of failures. Then mechanical failure, that means on hard disk a spindle, a pin will be there which reads the disk, that rotation or rotating or the spindle related failures comes under the mechanical failures. So these are the different types, common types of the disk failures. Then comes to the latent sector errors. The errors here are majorly of two related to the data security or data integrity or data protection. So the errors are of latent sector errors, that is LSE, and another is the block corruption. So here once you observe the hard disk how it will be, this is the disk where the data will be stored, and this is the suspension and the pin which reads the data. This will work as same as the gramophone record which we see in earlier ages, and there will be a voice coil motor, a motor will be there, and pivot will be there, which gives the connection to the suspension to the point, then head, then comes to the spindle motor, so that it will rotate, the disc will rotate, the tracks will be there on the particular discs. Okay, so these are the things. So here on the, it will be divided into sectors, and this, here there will be a small block. This block is the storage. This block will be corrupted. This block will be corrupted. So the corruption of the block, there are two types of errors. One is the latent sector error, another is the corruption. There are two types of hard disk. One is the cheap and another is the costly. That means the durability of the costly will be very high comparing to the cheap. So the LSE error percentage for the cheap is 9.4%, whereas the costly hard disk, it is 1.40% only, and the block corruption is 0.5% for the low price hard disk, whereas the higher prices hard disk will have the corruption level of 0.05%. So this is the hard disk, how it will look like. This is, here there will be a circuit board, here there will be an IC. The failures related to the firmware will be here. Then comes to the, this is the spindle, this is the rotator or the motor, and the disk is this one. So this is the general how the hard disk looks. So here LSE, we can arise a disk sector has been damaged in some way, means the data will be crushed. It may be a head crash or something due to unexpected damage. The bits stored in it may not be readable. That comes under the block corruption. So here the disk failure chances are of mainly head crash, then bad sectors. So these are the sectors. So here the disk is, we can see the tracks on the disk, and then the sectors, the divisions, sector of the track, and clusters. So in the cluster, a small part of cluster, we can consider it as a block, and this block will be corrupted, and related to it we are discussing right now. So here the hard head crash, there are chances of head crash, then there is a chances of bad sectors, then disk failures, circuit failures, bearing and motor failures, miscellaneous mechanical failures. Then comes to the how it works and how it will be when we can check it, as how it will be incorrect. That means the data checking methods. So here disk error checking codes, and the cyclic redundancy check is the most common checking method for the block corruption, and the other methods are error correction and code. So in this particular session we are going to check about the checksum method. By using checksum method, how to check the data which is stored is that we are going to get, and how the data will be stored in the particular hard disk. So here the cosmic rays can also flip bits leading incorrect contents. That means some magnetic rays or some other rays may also damage the hard disk. Fortunately, in disk error correction codes ECC are used by the drive to determine whether on disk bits in block are good, and in some cases to fix them. So here we have a chances to, if a block is corrupted, that block can be moved to the, if a part of block, this block is corrupted, that can be moved to the another place. So Okay, so the we can fix them. The block can be shifted from one place to another, and we can fix them. So the next thing is latent sector errors, which refers to the situation where the particular sector on the drive be inaccessible. If it is inaccessible, make it can keep a situation where we cannot access it. So LSE or a critical factor in data reliability, and it may cause encountered during the RAID construction also. So the disk failure, after a disk failure in systems without redundancy, a block corruption includes the cyclic redundancy check, that is CRC, as well as the error correction code, ECC. Then the frequency of latent sector errors, that is LSE, costly drive with more than one LSE or likely to develop additional. For most drives, annual error rate increase in year 2. LSE increase with disk size. Most disk with LSE has less than 50. So the disk with LSE are more likely to be additional LSE. There exists a significant amount of spatial or temporary locality. Disk scrubbing. Disk scrubbing. Disk scrubbing is useful. So we are going to discuss regarding disk scrubbing later. Most LSE will found this way. Next comes to the block corruption, which is the most important. So here there are two types of error, two types of data errors, that is the LSE, latent sector errors, and block corruption. The chances of block corruption varies generally across different drive models within the same drive class. Age effects are different across models. Workload and disk size has little impact on corruption. Most disks with corruption only have a few corruptions. Corruption is not independent with a disk or across disk in RAID. There exists spatial locality and some temporal locality. There is a weak correlation in LSEs. So here we can see how the tracks, you can see how the tracks will be there, spandrel will be there, disks will be there, how they are arranged. Okay, let's see the handling of latent sector errors. Latent sector errors are easily detected and handled using redundancy method. RAID and RAID 4 and RAID 5 system based on parity. The system should reconstruct the block of from the other blocks in the parity group. Then detecting corruption, that is the checksum. So how the data is corrupted, when to check it, the mechanism is known as checksum. The client can tell the block has gone bad by using the checksum mechanism. By using the checksum only, we are going to tell that the block is bad. So here to identify the checksum, we have the procedures, that is simple, the result of the function, the chunk of the data as input, and computes a function over the data producing a small summary of the content. So for the data is stored in the disk, it will give a checksum. Based on the checksum only we can identify whether the data we given is as same as the data we received. The major concept here is the data which we stored should be retrieved as that of the same. That is nothing but the data integrity and protection. So this is the example concept where we taken a 16-bit 4 4 4 4 16. Okay, so here 365E. So I am taking 365E. This is an hexadecimal notation. What is an hexadecimal notation? See here, you may know 9 decimal, after 9 then there will be 10. So the 10 will be called as A, 11 will be called as B, 12 will be called as C, 13 will be called as D, 14 will be called as F. Sorry, A, B, C, D, E, and 15 will be called as F. Since the hexadecimal is base is 16. Hexadecimal base is how much it is? 16. Up to 15 the values will be taken place. So here the value is E. Here the value is E. E value is 14. So the value here is 3, 6, 5, 14. Okay. So 3 in binary digit is 0, 0, 1. 1. 2 to the power of 0, 2 to the power of 1, 0, 0. 2 to the power of 0 equal to 1, 2 to the power of 1 equal to 2, 2 plus 1 equal to 3. So here the value you can identify that 3 value is 0, 0, 1, 1. This is 3. Then 6 value. 6 value, 6 divided by 2, 2 3s are 6, 0, 2 1s are 2, 1 remainder, then again 2, 0, 1. So output is 0, 1, 1, 0. The value is 6. Then comes to 5, 5, 2, 2 1s are 2, 2 2s are 4, remainder 1, 2, 1s are 2, 1, 2, 0, 1. So 1, 1, 0, wait. Here 0, sorry. 5, 2, 2, 2s are 4, 1, 2, 1s are 2, 0, 2, 0, 1. So the output is 0, 1, 0, 1. So here you can see 0, 1, 0, 1. Next is 1, 1, 0. So what is 1, 1, 0? That is E, 14. 14 you have to calculate 2, 2 7s are 14, 0, 2, 3s are 6, 1, 2 2s are 4, so 2 1s are 2, 1, 2, 0, 1. So 1, 1, 1, 0. So here 1, 1, 1, 0. Like that, this total component, 16-bit component is equal to 365E, and this 36, this component which is C4CD is equal to this value. So 110, 110, C4D. Like that, here this is BA14. So like this, 4 set of components are given, and we are going to find the checksum. What we are going to do, we are going to find the checksum. That means first what we did, we converted an hexadecimal to the binary. What we did, we simply converted the hexadecimal to the binary 16-bit as of for a group. And as a for a group, we are going to create a checksum which by using the XOR. What is the formula of XOR truth table when you check A, B, C, that is the answer. So 0, okay. So let's take XOR 0 0, it will be become 1 1 1, it will be 1 1 0, it's 0 0 1, it's 0. This is a truth table for the XOR. Let's check it here. What values we had? We had the values of 0 0 1 1, 1 0 1 1, 1 1 1 0, 0 1 0 0. So here 1 1 it's 0, 1 1 it's 0, 1 1 0, and again 0 1 1, 1 1 it's 0. So the output is 0 0 1 0. So we got 0 0 1 0 in the checksum. So this checksum is working based on the XOR component. The output, total output we received is this one. That is 201B9403. We will check this last component whether it is equal to 2 or not. So what is the output we got is 0 0 1 0, 2 to the power of 0, 2 to the power of 1, 2 square, 2 cube. So only this is 1. So 2 to the power of 1 equal to 2. So the output is 2. So here it is 2, then it is 0, then it is 1, and this is B. So this is the total checksum. So by using this particular method of XOR, we calculated the checksum. XOR is recognizable checksum, but with some limitations. Next, this checksum addition. So its approach has an advantage to being the fast. Compute 2's complement addition over each chunk of the data. We have to ignore the overflow. Then Fletcher checksum. Compute the check bytes S1 and S2, assuming a block D consists of bytes D1 to Dn. S1 is simply in turn is S1 equal to S1 plus Di mod of 255, that is compute the overall Di. Then S2 equal to S2 plus Si S1, that is mod of 255, again overall Di. Then comes to the another method which is known as the cyclic redundancy check. So here treating D is the bigger binary number, divide that by an agreed upon value. The remainder of this division is the value of the cyclic redundancy check, that is the C or C. So now related to the checksum layout, how the layout will be there. Here the check disk has the data of D0, D1, D2, D3, D4, D5, D6. And now with the checksum list, that means some part will be given to write the checksum. This part will be given to write the checksum. When we observe here, this is the data which is converted into the binary digit, and this is the checksum, and when it is converted to hexadecimal. So here this is a particular block, means this is D1 and this is D2. This D1 has a checksum, this one, and the D2 has a checksum is this one. So let's take an example. So this is D1 and this part is the checksum. And next is D2. This part is the checksum. So when you observe the previous problem, here this the total part is D1 and this total part is D2 and this is the checksum and this is the checksum. So the structure of this will be like this: D0, D1, D2, D3, D4, D5, D6. And the disk layout is with the checksum. That is, this is the checksum place where you are going to use. For an example, simple example in data structures, you will have a linked list. In linked list, there will be an address block and there will be a data block. Here also, there will be a checksum and there will be a data. Data is denoted by D0, D1, D2, D3, D4. And checksum will have, every data block will have a checksum. And to store the checksum packed in 512 bytes, the checksum will come before and all will be as a packed. So, how you are going to use the checksum? When the data is transferred from one place to another, it will be transferred as a pack. So the particular data will has a checksum. And as for the security reason, protection, no one should read the data. Even the system cannot read the data. The verification, the editing will be done through the checksum, not with the data. So based on the checksum, the editing process will be done. So this concept comes under the data integrity. We are going to integrate the data with the checksum for the sake of the protection. So here, when reading a particular data block D, the client reads the checksum from the disk CS of D, that is the stored checksum. And when the checksum is received at particular stage, that is the computed checksum. Okay, so first stage when it is stored, it is called as the CS of D, that is the storage. When it is retrieved, CC of D. When it is retrieved, it is called as CC of D, computed checksum. When it is stored, it is called as the stored checksum, CS. When the CS of D is equal to CC of D, then the data is safe. If this checksum does not matches, data is corrupted. If this checksum does not matches, data is corrupted. So this is all about the checksums. And there are other methods which here we are going to see is a new problem, misdirected writes. Modern disks have a couple of unusual failure modes that require different solutions. Misdirected write arises in a disk and RAID controllers which the data to disk correctly expect in wrong location, that is disk 1, disk 0, D0, D1, D2. D0, D1, D2 is the disks. So the most important concept here is the next is the disk scrubbing. Disk scrubbing is the most important concept here. So here, when do these checksum actually be checked? Most data is rarely accessed and then remain unchecked. The remedy to this problem is mainly system utilize disk scrubbing, a periodically reading through the every block of the system, checking whether the checksum is still valid, reduce the chances that all copies of certain data become corrupted. So the method which used to check the data periodically and check whether the checksums are still valid and reduce the data corruption, the concept is called as disk scrubbing. Next, overhead checksum. The overhead checksum is majorly depend upon the space and time. So the total optimization techniques related to the space and time. So if you reduce the space, automatically your time will be increased, and every mechanism used for the in the computer system is to reduce the space as well as to reduce the time to for the process. So here the two kinds of overheads, one is the space and time. Space overhead, disk itself. What is the space overhead? It is the disk itself. The typical ratio be 8 byte checksum per 4 KB data block, and for 0.19% on disk space is the overhead, whereas the memory of the system, this overhead is short lived and not much as concern. The time overhead is of CPU must compute the checksum over a block to reducing the CPU over the combined data copying as well as the checksumming in a streamlined activity. So now we are going to discuss the final concept, that is the data integrity and protection. The protection is a mechanism for controlling the access of programs, process or the users to computer system that is the resources. This mechanism must provide a meaning of specifying the controls to be imposed as well as means of enforcement. Protection includes data integrity with a requirement to detect, prevent, provide alerts for all attempts of unauthorized changes to the data, to include both operating system critical data files and user data. Data integrity is a concept and process that ensure the accuracy, completeness, consistency and validity of the organization's data. By following the process, organization not only ensure the integrity of the data but guarantee they have accurate and correct data in their databases. Data security includes protecting data from unauthorized access and preventing data from being corrupted or stolen. Data integrity is typically a benefit of data security but only refers to data accuracy and validity rather than data protection. So, by this, I am concluding my session related to the data integrity and protection. Hope you all understood well the major concepts of data integrity and protection. Thank you, one and all.